the calendar, they all seem to be online. So,
They did it? I thought they were in person. I might be wrong.
or sorry, yeah, in person.
I was gonna say I
yeah.
thought they were in person.
So yeah, I mean, like I'm optimistic that it's sort of like the worst of this is done and we're going to start getting back to normal. And it's the first time I've kind of been optimistic about that in 2.5 years. But yeah, I think we're getting to that point where people are like, okay, it's getting endemic. We can live with it. So yeah, I think we'll be entirely in person for 2022, 2023. Karina, interesting question. So I now have approval from the associate chair to do a 24-hour exam. I am going to start drafting up the wording for a syllabus change because they've said, if you're going to do it, we'd like you to do a full on syllabus change and all of the bureaucratic stuff that goes with that. So I'm going to start drafting that up. And so you'll hear about that probably more tomorrow. So Brandon, right now I have to put it to a vote. So it has to be put to a vote for the class because right now the syllabus says it's a 3-hour exam. So we will put it to a vote for the class. That vote will happen next week-ish. I'll probably just do it through Quirkus rather than an in-class vote. And yeah, so, and then, by the end of next week, we should know definitively what the result of the vote was. Yeah.
Do we know if the vote has to be what is it, like a 2-to-1 split, or is it just a 50-50?
51% has to vote in favor. Yeah, that's it.
Okay.
Mm-hmm. Yeah, I mean, a supermajority versus just a majority. Yeah, I mean,
some decisions, at least I remember when it was the student union, I'm not the biggest fan of, at least in ETM, were made to be on like a 2-by-1 ratio.
Yeah.
For voting to go through. So you needed 67% to actually get a specific vote to go your way, not 50%.
Yeah, and like legislatively, sometimes it depends, right? Like there's some legislature that only requires a simple majority, some require supermajority. Often, like really impactful things require supermajorities, right? So yeah, like changes, for example, to the Canadian Constitution, I think, requires supermajorities, right? Right, yeah. And actually, yeah, and I'm pretty sure it's very similar to Canada in that you need like 6 out of 9 provinces, because apparently the territories don't get a vote in constitution changes. So to make constitutional amendments, or like to change the Constitution Act, I think requires 6 out of 9 provinces. So there's stuff like that as well where you have supermajorities, because this was a big thing when we were looking at reforming the Senate, the Canadian Senate, and they're like, oh, well, what would we actually need to do that, right? What's the actual date of the test? It's like 1 to 4 on the 23rd or 22nd? 22nd. So it would start the day, but like the test has to end when the test would have ended. Does that make sense?
So it'll be the day before to the day of, to that time spot.
Yeah, so it'd be 4 p.m. on the day before until 4 p.m. the day of the test. Yeah, so 4 p.m. Thursday to 4 p.m. Friday. Oh, we haven't decided yet. We haven't made it. We probably won't make it until a fair bit later. Yeah. Yeah, once we know. So we're talking about we're talking about the poll question that's currently on the screen. But no, some people are asking about like the final exam. I did get first level approval to make it a 24-hour exam. So we need to vote on that and stuff, but I can start the wheels turning. No, because I mean, like, Brandon, you don't know there's just no value in making those tests that early, because you want to be flexible enough that if if you fall behind in some material, or, snow days. When we were in person, snow days used to be a thing. And so you might miss a week or a class, or one, right? If you were like MAT133, one section might miss a day of class and another one didn't. So you had to be flexible enough that you could maneuver around that. Now that we're online, we're actually can basically wait till 2 weeks before the exam to submit the exam. But when you're in person, usually exams are due beginning of March, because they have to be test read and printed and all that stuff, right? So
it's the printing that takes a long time.
Yeah, exactly. Because so you guys might not know this, but the registrar's office does all final exam stuff, right? Like I have nothing to do with it when we're in person. Excuse me. So they need to get your final exam. It needs to be proofread, and then it needs to be approved, and then they print off a bajillion copies of it. They have a massive vault where they keep all the tests, and then they bring it to the room, they administer it, they take everyone's signatures and everything. So as the instructor, you have actually nothing to do other than you made the test. But all of that means that this stuff has to be started well ahead of time, right? Because it takes a lot of time to organize the logistics of that. And yeah, Piazza will still do, it'll be the same, just like it'll be the same as a test, right? It might be a little bit longer, but it's going to be we're aiming for the exact same format of the test. And it'll be at a slightly different time. Right? Instead of 9 to 9, it'll be like 4 to 4 or something. Well, I'll release more details like when we get closer.
I feel like the worry should be about the test today.
That's true. That is true.
Yeah,
you got to test in like 4 hours here. So, but I mean, like, there's nothing to worry about for that test, right? Like they know what it's going to be on, they know what its format's going to be, and it's just the questions now. Okay, I'm going to lock this up in like 20 seconds because we've actually let this question go for a really long time. Okay. All right, yeah, overwhelming majority of the class said A. A is absolutely the correct answer. This is one of those things too. Remember, for all these like antiderivative questions, you can check your answer, right? Because if you're trying to figure out which of these, in this case, A, is the antiderivative, all you have to do is differentiate it, right? And see if you get the answer that you started with. But let's pretend that we didn't know to do that. That's actually a lot of work, right? Like if you wanted to differentiate all 4 of these answers. So if you weren't going to do that, what would you do, right? Like how would you do it? So this is question 6. So we've been given this function. What do we call it? G of S is 10s 1 over the square root of s. Okay. Now, this stuff of anti-differentiation isn't just, some sort of nice thing that we can do. This is basically what we're going to be doing for the rest of the year, right? Is largely this sort of stuff. So we really want to make sure that we're comfortable understanding this process that we're doing. Now, the antiderivative, if you watched the videos, you learned a couple of things. One, the antiderivative is linear. So the antiderivative of the sum of 2 functions is the sum of their antiderivatives. So we just need to find the antiderivative of each of these functions separately, right? So let's find the antiderivative of each function separately. Okay, so let's start with 10 to the s. No worry, Emma, don't worry about it. So with 10 to the s, what we want to do is we want to think like, okay, do we know a function that differentiates close to 10 to the s? Like it doesn't need to be perfect. It's just got to get close. Yes, I am that we don't know that yet. So you're getting a little bit ahead, but yes. Okay, so we don't, right? Like even if you don't know exactly what the antiderivative is, you just want to get close because you can kind of tweak it, right? Like you can fix it once you've got the meat and potatoes, right? Like you're not worried about multiplicative constants. So the thing about these exponential functions is that they differentiate to themselves, right? So if I take the derivative of this, I get 10 to the s times ln 10. Now I want my output to just be 10 to the s, right? Because that's what I'm trying to find an antiderivative for. I'm trying to find a function which when I differentiate it just gives me 10 to the s. not 10 to the s ln 10. But the fix to this is no problem. What we're going to do is we're going to take this ln 10 thing here, and we're going to go, whoop, and we're going to move it onto the other side, right? So we've got that will now just give us 10 to the s. So this says that this is an antiderivative for 10 to the s. Okay, and of course we could, throw, where's the ln 10 come from? So you have to recall, in general, the derivative of a to the x is a to the x ln a. So in this case, a was 10. Right, so it's just whatever the base is, yeah. Excuse me. So that's the first function. Now for the second function, 1 over the square root of s, the key there is to write that as a power, right? So we're going to say, okay, for 1 over the square root of s, we're going to write this as s to the negative 1/2. And the reason why we do that is because we actually have a formula for how to differentiate, or sorry, anti-differentiate s to the n, right? So recall, right? So that tells us that if we want to find an antiderivative for x to the n, then we use this function right here. And yeah, exactly, Simon. Yeah, we're going to use that thing from that table that I gave as part of the video. So I gave this, right, and in the video, I give like a big table of like common antiderivatives. Again, it's important to know where that table comes from because I don't necessarily want you to memorize it, but just, have a good idea of like where these constants come around and why they show up. So in this case, here we have n is negative 1/2, right? So if we add 1 to that, we're going to get positive 1/2, right? Negative 1/2 plus 1 is positive 1/2. And now if we use, our table, or this fact that, we know what the antiderivative is from this formula, this gives us 2x to the 1/2 is x to the negative 1/2. So here, that's our antiderivative. Okay, and if you want to just use the table, you can. Maybe you're kind of like bothered by the fact that I put the derivative on the left-hand side, but that's just the definition of the antiderivative, right? It's the thing that you differentiate to get the right-hand side. Okay, so here now I've got my, here's one antiderivative, and here's the other antiderivative. So antiderivatives, that's not how you spell derivatives of 10 to the s plus 1 over root s look like, and remember, antiderivatives are only unique up to additive constants, right? So it's going to look like 1 over ln 10 to the s plus 2s to the 1/2 or root s plus some constant, right? And if we go through all of those options in the table, there's only one of them that looked like that. It didn't have a big plus c. It had a particular constant, but whatever. We know it's just some constant there. And the one that satisfied this was a. Okay? So that's how we do that. Again, in something like multiple choice, you can check just by differentiating. So if you wanted to do that, that's totally a valid solution. Otherwise, though, most of what we're going to do isn't going to be checking that something is an antiderivative, but rather, actually computing it from scratch. Okay, so are there any questions about that? No, we're okay. All right, let's do the next one. Now, as much as I said, you should actually try and compute it, this next one is actually too hard for us to compute. So you don't know how to compute this yet. So as a big hint for this one, you actually should look at the functions that I've given you differentiate them and tell me which of these functions, when you differentiate it, gives you ln x, okay? Because we don't know how to find an antiderivative of ln x right now. We need some more sophisticated tools in order to be able to do that. So yeah, interestingly, we can use this question almost like a practice for today's test, right? Because today's test is how well can you differentiate? And this is really now a problem of, how well can you differentiate? Okay, let's do 30 more seconds. Okay, 5 seconds, get those last minute answers in. Yeah, this is a cool one. I like this question. I like this one a lot. And it speaks to something, right? So we're gonna, we can talk about this too. So the class is leaning towards D. A couple people said B as well. And there's a little bit in A and a little bit of C. Okay, now A, you probably made a mistake and you differentiated little f, right? And you wanna differentiate big F, right? You don't want to differentiate little f. You want to say which of the big F's do you differentiate to get little f, right? So if you answered A, I imagine that's what you did. And then the rest are just sort of interesting examples in the chain rule. So let's give that a shot. Okay, so for letter A, so this is question 7. Okay, so A was this function. And hopefully you all realize like the +3, -10, +5, whatever those are, those constants don't mean anything, right? Because you're going to differentiate them. And when you differentiate the constant, it just becomes 0. So really the meat and potatoes of this is not the constant part, right? So if we differentiate, we're going to get f prime of x is -1/x². That's not what we want, right? We want that capital F prime is equal to ln x. So A is not correct. Okay, so B, what do we have? 1/2 ln x². -10. Okay, so if we differentiate this one, we're going to get ln x over x. Do y'all see that? Because I think some people who might have said this one, you did the first part correct, right? Like you brought the 2 down and then you got the ln x, but you have to remember that you have to, by the chain rule, differentiate the inside function as well, which in this case is ln x, right? So when you differentiate the ln x, you get a 1/x term. So the derivative of this thing is ln x over x. That's still, unfortunately, not the correct answer. So it's not this one either. Okay, so C, we've got ln x² +5. Now, something cool is going to happen here. Some of you might see the trick to do this one really quickly. Okay, so there's a way of differentiating this one super, super quick. But let's say you didn't see it. Let's just kind of do it using the normal chain rule. So we get 1/x², right, times the derivative of x², which is 2x. And that gives us 2/x. That's not ln x either, right? So that's not it. And if you didn't see it, the trick to this is you all know that ln x² is 2 ln x, right? You can pull the 2 down in front. Now you don't even have to chain rule this anymore, right? It's just 2 times ln x. So the answer is 2/x. Can I do? Okay, yeah, hold on. There's a couple of things here. So first I was asked to do B again. So let me maybe expand myself out, give myself a little bit more space here. Okay, so first of all, so yeah, we're looking at B some more. Let's ignore the -10, right? When we differentiate that, we find a 0. And Simon, I'll come to your question in a second. Let me do this first. So we're just looking at 1/2 ln x², right? So when I differentiate 1/2 ln x all squared, what are we going to get? We're going to get 1/2 times 2 ln x to the power of 1 times the derivative of the inside, like this. Does that make sense? Do you see the chain rule working there? And so our 2 and our 2.5, right, just give us 1. The derivative of ln x is 1/x. So what do we get? We get ln x times 1/x. And that's why we get ln x over x, right? I just kind of like put them into a single fraction, but you get ln x times 1/x. So does that fix that for you? Make sense now? Cool. Okay. Now the other question is, so I got another direct message saying, I'm confused. Aren't we trying to find the antiderivative? Yes. Okay. So remember, we've got this function. So here, let me put this in yellow so we can just sort of distinguish it. Right? So an antiderivative of this function, maybe let me give myself a little more room here. An antiderivative is a function capital F such that the derivative of capital F is equal to little f, right? It's the opposite direction of differentiating. We're not differentiating little f. We're trying to figure out what function would we differentiate to get little f, right? And so what we're trying to do here is we've been given a bunch of examples of big F's. In order to figure out which of them is an antiderivative of little f, we can just differentiate them, right? We can basically test this. So if we compute the derivative of big F, If it's equal to little f, then we've got an antiderivative, right? So in each of these cases we're going through, I'm computing their derivatives. So far, none of them are ln x. That tells me, by process of elimination, the answer is probably D. But does that make sense, direct messenger? Right? So I'm brute forcing my computation of the antiderivative by just checking, is its derivative equal to little f? So we're trying to find which of these functions differentiate to get ln x. Yeah, exactly. Yeah, that is what an antiderivative is. It is a function which would differentiate to become ln x, right? So it's like you're being given the answer, right? So like this test that you're going to write today is I'm giving you the function and I'm saying differentiate it. Anti-differentiation is I'm giving you the answer and I'm asking you to give me the function to differentiate. Do you know what I mean? So I've given you ln x, and now I'm saying, tell me what I would differentiate to get ln x out. That's why it's called anti-differentiation, right? It's the opposite of differentiation. Okay, so by process of elimination, it's probably got to be D. So that's x ln x minus 4. Okay, let's try this. So let's differentiate. So I've got to use the product rule. No problem, no problem. So I've got to use the product rule. So I'm going to do the x ln x term first. So it's the derivative of the first, which is just 1. Maybe let me put the 1 in here so you can see what's happening. 1 times ln x. So derivative of the first times the second plus, here's something really cool that happens, right? So the derivative of the second times the first is x times 1 over x. Okay, so that's this part right here. And then I get minus 1. And look at what happens. So if I simplify everything, I get ln x plus 1 minus 1. The plus 1 and the minus 1 cancel. And that just gives me ln x. Boom, there it is. That's the function that we differentiate in order to get ln x. So this is the correct answer. Okay. So there's this cool little, this is surprising, right? Like, look at what had to happen. We had to have some sort of magic cancellation going on here. And this is one of the things, when you hear people talk about calculus, one of the things they talk about is that integral calculus, which is what, we're doing. Integral calculus, and we haven't seen, in all fairness yet, you haven't seen how antiderivatives are related to integral calculus. We're going to learn that next week. But this process of anti-differentiation is much harder than differentiation, right? I am extremely confident that if I gave you all the function ln x and said differentiate it, every single one of you here could do this, right? I certainly hope so, because you have a test tonight. So if I said just differentiate ln x, you all could do it. But now if I say anti-differentiate, suddenly your answer looks like this. What the heck? How could that possibly be true, right? And more importantly, how would you be expected to know that? How would you find that? So we're going to teach you next week some tools to show you how you would be able to do that once we've learned the fundamental theorem of calculus. But it turns out the process of anti-differentiation, which is most of the computations that we're going to be doing for the next couple of weeks, the process of anti-differentiation is significantly more complicated than differentiation. Significantly more complicated, okay? Because what we're going to find, let me give you a quick little example. Does anyone see an right, yeah. And you'll figure out what IBP is later. So can anyone tell me, can anyone see an antiderivative for this function? So we haven't learned how to do it. Some of you might have in high school learned how to anti-differentiate this function, but can anyone just eyeball it? Can anyone just see what an antiderivative is? Ooh, that's an interesting one. That's a good guess. I think though what you might have done was split it in a weird way, you kind of split the fraction up. And that one doesn't quite work. Because what I would suggest, Agam, is try differentiating that. And if you differentiate that, you should just get 1 over x, right? So I can see what the answer is. Let me write it down for you. Right? Yeah, it's okay. You're still learning how to anti-differentiate for the first time, right? Like it's totally okay. And it's the opposite of what we've been doing for the last couple of weeks. It takes some time to get used to. 100%. Don't worry. Even when we start talking about integrals for the first time, I have to remember like, okay, I need to go the opposite way now, right? I'm not differentiating anymore. I'm going the opposite direction. So an antiderivative of this function is ln 1 plus x squared divided by 2. Okay, and you can check that pretty easily by differentiating it. Yeah, I'm going to change this just a titch, just the smallest little bit. Okay. So instead of having an x in the numerator, I now just have the number 1. And in some sense, this might seem as though it's actually easier, right? Somehow the function is an even nicer function. It's a more straightforward function. This should be easier to anti-differentiate, right? And no, the answer is it's so much worse. Some of you might have written this as this in your time. Right. Like we don't even do trigonometry in this class. Here is a function that on the surface of it does not appear to be related to trigonometry in any way, shape, or form. And yet, boom, somehow we needed trigonometry in order to solve it, right? And so the process of finding antiderivatives significantly more complicated than finding derivatives. It's just kind of a sad and unfortunate reality. Maybe let me ask you the following. Can anyone tell me an antiderivative for this one? Because you know that function, and I promise you there is no, that would be a lie if I said that. Can anyone tell me what, give me an antiderivative for this? It does have one, strictly speaking, there is one. But you're like, wait a second, the way you answered that is a little weird, right? Like, what do you mean strictly speaking? So there is an antiderivative of this function. Okay, it does exist, but we cannot write it down using exponentials, logarithms, trigonometry, polynomials, roots, powers, anything like that. It does not have an elementary antiderivative. The antiderivative of this function cannot be written down using any of the functions that we know. Yeah. Okay, it is impossible to express an antiderivative of this function in terms of any function that we know. We can define a new function. We actually do. So we do define a brand new function. No, because e to the x times e to the x. So I got a question, which is, can't we write it as like this? And no, because this is e to the 2x, right? This isn't e to the x squared. E to the x squared is like e to the x to the power of x, right? So we do define a brand new function which is its antiderivative, effectively. We call this thing ERF, which is a silly name, but we call it ERF. And the derivative of ERF of x is e to the x squared. We define ERF to be the antiderivative of this function. Okay, so that's actually something we do. We don't have the means to write this thing down. We can plot it. If any of you go and you ask Wolfram Alpha to plot ERF, it will plot ERF for you. But like you can't write it down in terms of logs, cosines, sines, polynomials, anything like that. It doesn't work. You can't write it down. Okay. And then here is, yeah, exactly. Yeah, absolutely. Somebody said, hey, isn't this like the error function or something? Absolutely. That's where ERF comes from. It is the error function. Exactly. Yeah, and ERF stands for error function. So here's the other crazy thing. Now, strictly speaking, we haven't learned how to integrate, from this is, let me say this. This is one of the most important functions in the world. Actually, if I change it just a little bit, if I throw a minus sign in front of there, this is one of the most important functions in the world. Why is this one of the most important functions in the world?
Bell curve.
It's the bell curve, right?
Yep.
When you guys like talk about, oh, you're going to curve my grade or something, when you talk about normal distributions, when you talk about Gaussians, like this is the bell curve.
That's a very cool function for sure.
Right? That's poorly drawn.
That's
this is the, yeah, it's the
bell curve.
It's the normal, yeah, it's more or less, this is my version of the bell curve. This is the most, right? Like it basically, if you do things like sample people's heights, it looks like this. If you sample people's grades, it looks like this, right? Like if you sample a sufficiently large size of independent and identically distributed events, it should look like this. So this is one of the most important functions in the world because it just shows up in absolutely everything. And you remember when we were doing probability and statistics, we just did like finite discrete things, right? Like we flipped coins and stuff. But you can imagine when you get into like more complicated statistics, you need to do continuous statistics. So this becomes, remember we talked about probability functions, like probability distribution functions. This is the probability distribution function of a normally distributed data set, right? So you get this. Now here's the crazy thing. This is also one of my favorite facts of all time. I just showed my 257 students how to compute this. Okay, and yeah, it took until 257. So it takes until, if you want to do this properly, I think some of you will learn this in like your second year econ stats class, whatever it is. I don't remember what it is, the one that Nick teaches. Yeah, whatever one it is. So this is true. Okay, so the area under that thing, right? Remember, it looks like this. Looks like a little hat. And we say, what is the total area under this curve? Does anyone know what it is? It's not one. So it is one if it is actually, it's one if it's actually normalized, right? And it's actually a proper probability distribution. So a proper Gaussian does have the factor in front of it to fix it. So it is one, but yeah. So Simon, you are right, because again, you know that antiderivatives and integrals are secretly related. But yeah, this actually has a number. And the question is, do you know what number this is? And if any of you go to Wolfram Alpha and you plug it in, you're going to be like, what the hell, right? You're going to see this and you're going to be like, that's nonsense. There should be no way that this is true. And the answer to this is the square root of pi. Okay. And you might say like, okay, that's nice and all, but like some of you, okay, I'm glad that there are a couple of people out there who are like, what? But for those of you who aren't like, what? Okay, yeah, so first of all, you can definitely square root pi, but second of all, where the hell did the pi come from, right? Where did the pi come from? There's like, what do we think about when we think about pi? We think about like circles, maybe some triangles, maybe some trigonometry, some sines, some cosines, things like that. Where is the, like, how did a pi show up, right? And the answer is there's secretly trigonometry. There's hidden inside. And maybe here's the like really cool, here's a really crazy fact. The exponential function is a trigonometric function. E to the x is secretly sines and cosines. Okay, and you can't see it. It's really hard to see, but e to the x is actually sines and cosines. E to the x, they are the same thing. It's related to Taylor series, but it's not quite. Like they are, you can use Taylor series to help you see that they're related, but you don't strictly speaking need them. There is no difference between e to the x and sine x. They are effectively the same function. And that should be bothering you because you're like, no, they're not. They're totally different. E to the x goes and like explodes, and sine to the x is just like willy wavy and doing whatever it wants. But no, they are the same thing. It turns out they are the same thing. And that's why a pi shows up. Okay. Yeah, Taylor series it's a really cool thing. We actually used to do it in this class a little bit. It's a way of writing every function as an infinite polynomial. That's what Taylor series are, right? It's just a way of doing that. Here's something else. You want to know something else that's crazy? So without me using sigma notation, because I know that bugs you. Okay, but what I'm just doing is, I'm doing this, right? So hopefully you guys see the pattern. Yeah, exactly. So hopefully you guys see the pattern, right? It's just 1 over the number squared, right? So 1 plus 1 over 4 plus 1 over 9. So the denominators are just the squares of the natural numbers, right? So the next one is 1 over 49, and then 1 over 64, 1 over 81, 1 over 100, so on and so forth. This is pi squared over 6. Right? And yeah, so again, like how? Right? Like, how is that possibly true? Like, how could, when you add up all these numbers, pi squared over 6? And I don't mean that stupid thing, like it, number file or whatever those guys' names are, those guys blow me insane because they did the stupid thing where they show you all that this is true.
Oh, the minus 1 over 12 thingy?
Yeah.
Oh, I know the one.
So this drives me insane because this is not true. Okay. It is true, but in a very loose interpretation of what the addition sign means. This is nonsense, okay? And this drives me insane because people like Numberphile use this for clicks. And mathematically, there's a rigorous way of making sense of this. But obviously, if you added together a bunch of positive whole numbers, you don't get a negative fraction, right? That's nonsense. This, though, okay, so I don't even want that on the screen. That's total BS. This is true exactly, it's an analytic continuation of the Riemann zeta function. This is true. Plug those numbers in, okay? Go to Wolfram Alpha and just plug 1 plus a quarter plus a ninth plus a 16th plus 1 over 25th plus 1 over 36 and see what number you get. And then plug in pi squared over 6 and you'll see they're damn close. And the reason they're not exactly equal is because you didn't add 1 over 49. So if you add 1 over 49, you get a little bit closer. If you add 1 over 64, you get a little bit closer. This isn't a hand-wavy BS clickbait number file nonsense equal sign. This is an equal sign. These two things are equal, right? Like how, again, where does the pi come from? Isn't that crazy? Isn't that nuts? Like, how do you look at this and you're not just like, what is happening? And so this is what I'm saying. Like, there's actually a lot of really cool mathematics here that, we'll unfortunately never get to talk about, but there's stuff going on here that's really deep, really, really deep, really, really scary. Okay. So anyway, that's just kind of me losing it because there is a lot of really fun, really cool stuff here. And I hope you believe me, but most of you are probably just like, yeah, I'm happy to like hear about it from a distance as long as you don't make me actually do it, right? Yeah. Nice pun though. Yeah, I love that. That's good. Let me see if I can't get you another question here. You know what? This one gives a lot of students trouble. Let's maybe do this one. Yeah, that one. Simon, that's great. I love that. You should have given that one to the whole class. I would have. I think they would have appreciated that. Again, there is a sense in which that's correct, right? But again, it requires a very loose interpretation of what an equal sign means and a very loose interpretation of what a plus sign means. It is something known as the analytic continuation. In particular, it's the analytic continuation of something known as the Riemann zeta function. And if you go and you study calculus in the complex numbers, right? So we are doing calculus in the real numbers. If you go and study calculus in the complex numbers, analytic continuation is a very important tool and it totally makes sense there. But these like loose interpretations of what an equal sign are, this happens all over the place, right? Like the physicists are notorious for doing this. There's something the physicists do. This probably won't make a lot of sense, but there's something the physicists do. Let me just show you it here. The physicists write this. Okay, and this is nonsense. Okay, there's no way in which this is true. This is only true in the very loosest interpretation of what an equal sign is. So yeah, it's e to the 2 pi I x dx integrated from negative infinity to infinity. Now, this thing, this E, now you guys might be freaked out. You're like, wait a second, there's I's, and I don't even really know what an integral sign is. Yeah. Trust me, Anaga, that never goes away. And at some point you begin to question whether you actually understand stuff. There's something that happens right around you get to third or fourth year mathematics, if you're a math student, where you start to go, do I know anything? Is anything like sacred? And you question things like simple addition, you question things like simple multiplication, just because your trust has been violated so many times, right? No, it's worse than that, Brandon. So e to the 2 pi x, if you plot out this thing for different values of x, it just goes around in a circle. Okay, so that function just boop, goes around in a circle like this. And so if you integrate this function, i.e. you compute the area under this curve, it's nothing, right? It doesn't have a number because the function just keeps going around and around and around and around in a circle. So there's no way this is anything. This isn't equal to 1. It's certainly not a number. When the physicists use this, and they use this all the time, and the engineers do as well, when they're doing this, what they're doing is we're not playing with numbers and functions. The thing on the right-hand side is what's called a distribution. And the distribution 1 happens to agree with the function 1, happens to agree with the number 1. But this is an equality of distributions, not an equality of numbers. And this is related to the Fourier transform. So if any of you ever learn about the Fourier transform, this is because the inverse Fourier transform of e to the 2 pi I x is equal to the number 1, but does not evaluate to the number 1. It's equal to the distribution 1. So this is a tricky thing here, which requires understanding that this equal sign is an equal sign of things that most physicists don't know about, right? This is a Fourier transform, right? So I was asked, is this quantum? It comes up a lot in quantum mechanics. It does because it's used a lot. And the reason it comes up is because in quantum mechanics, you're looking at something called the Schrodinger equation, and solutions to the Schrodinger equation are solutions to a partial differential equation. It turns out most solutions to PDEs, or it's often easier to solve PDEs in terms of distributions instead of functions. So you say, okay, it's hard to solve things with functions, so I'm going to loosen my definition of what a function is, and now I have solutions. The physicists don't actually ever say those words. They just pretend that everything is okay, and they kind of, close their ear, like cover their ears, close their eyes, and go la 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 la. And so they pretend that it's actually equal to the number 1. And they get lucky because the math actually does work out. But for the most part, they don't understand what they're doing when they do something like that. It does. Because 100%, I can give you a place where 2 plus 2 is equal to 0. That thing totally exists.
Just depends how you define your field of elements.
Yeah, we'll work in Z4, right? All right, see you, Brandon. So Saeed, no, I don't. Actually, no, there's a place where that is true. That would be true in Z2, right? Because that's 1 plus 0 is equal to 1. So that would be true in Z2. Yeah. Okay, and everyone, let's do like 30 seconds on the question, then I'm going to take it up. Yeah, it's like, so you say that two things are equal if they give you the same remainder when you divide them. Okay, so in Z4, so in Z4, you say two numbers are equal if their remainders are the same when you divide them by 4. The same remainder when divided by 4. Right? So for example, 1 here is equal to 5 because those both have a remainder of 1, right? And if you do 2 plus 2, what is that equal? It's then equal to 0 because 2 plus 2 is equal to 4, but the remainder that you get when you divide 4 by 4 is the same as you get when you divide 0 by 4, right? And you might say, well, this is stupid. Like, who cares about this? Okay, first of all, this stuff is actually crazy important to do with like stuff like online banking, but it takes a while to see how this is related to stuff like online banking. And every time you make a transaction, you're secretly doing this stuff. But more importantly, you guys do this every day in your lives, anytime you work with a 12-hour clock, right? Like you all know that if I take 10 o'clock and add 4 hours to that, that's 2 o'clock in the afternoon, right? Why? Because 14 is the same thing as 2. Right? So 10 plus 4 is equal to 2. Why is that true? Because 14 and 2 have the same remainder when you divide them by 12, right? So these two things are equal in Z12. It helps what, people? Sam, I'm not certain what you're asking. Just saying there. Oops, no, I did not mean to save. Most people? Oh, I see. Sure, sure. No, it's all the way this is related. So by the way, B is the correct answer, everyone. So good job. Most of the class are getting B. The way it's related is when I, do online banking or buy something from Amazon or something, when I send my credit card information to Amazon, I want to make sure that that transaction is secure, right? That somebody can't steal my credit card while it's on the telephone lines getting to Amazon, right? And the way that we do that is by encrypting my credit card information. But that's actually really hard to do because you guys all probably, did you guys ever do things in school where like you wrote a code and then used it to send something to a friend and then your friend would decode it? Maybe that's something only nerds did, but like I can imagine some of you did that. And the problem with that is that you have to tell your friend how to decode the encryption, right? So you wrote a letter, you wrote a note, you encoded it, and then you gave it to your friend. No, sure, not these advanced things, but I mean like the problem with that system is that if I encode my credit card information and send it to Amazon, I also have to tell Amazon how to decode it. And in sending over the decoding algorithm, somebody could intercept that as well. So if they intercept both my credit card information and the method of decoding that credit card information, then they have it, right? So the big important thing here where math comes in very important is how can I tell Amazon, how can I encode my information and send it to Amazon, but I don't have to tell Amazon how to decode it, and only Amazon knows how to decode it, right? So how can I encode things without knowing how to decode them is the question. So this is called public key cryptography. This is called the RSA scheme. And this is how every single financial transaction on the web occurs. And it's all just math. So that's an interesting thing. If any of you want to look that up, it's called RSA, the RSA scheme. RSA is for the guys who invented it, and it's called public key cryptography. Okay. Okay, so this question, now a lot of students get this one wrong in my history because they make sort of a silly mistake. And I want to catch you on the silly mistake now so you don't make this at some point in future in your life. Okay, so we're told that F double prime is 15, and we said times square root of X. Let me just start, let's just immediately go X to the 1/2, right? Okay, and we're told two other pieces of information. We're also told that F of 1 is equal to 0. And we're told that F of 4 equals 109. That is an oddly specific number, right? And we want to determine what is F of 0. So what is F of 0? Okay. So what we're going to do, let's find an antiderivative of F double prime. And of course, an antiderivative of F double prime would be F prime, right? The first derivative. And the antiderivative of the second derivative is the first derivative. So I'm going to do this. And what am I going to get? So remember, I get 15 times what? 2/3 X to the 3/2. Does that look right? Did I anti-differentiate X to the 1/2 correctly? I think I did, right? And now here's an important thing. We have to include a plus C, right? Okay, so if I do this, I get 10x to the 3 halves plus c. So that's my first derivative. Okay, now I'm going to compute my second derivative. Oh, I think that person probably just didn't know that they were unmuted. So now I'm going to go back and I'm trying to figure out what f is. So I'm going to anti-differentiate again. So I'm going to get 10 times 2/5 x to the 5 halves plus cx plus d. Okay. And I do that, I'm going to get 4x to the 5 halves plus cx plus d, like that. Now what happens is a lot of students forget to put the c in here. Okay, they do all the antiderivatives and only stick in a single constant at the very end. But you have to include, every time you do an antiderivative, you have to put that c in there, otherwise you'll get an incorrect answer. Okay. All right, so I've got these two constants hanging around. And very conveniently, I have two equations. So I can use those two equations to figure out exactly what my constants are, right? So now I'm going to plug 1 into here. And if I do that, I'm going to get 4 plus c plus d. And then if I plug 4 into here, I'll get 109. Okay, somebody double check me. So the fifth, 4 to the 5 halves is 32 times 4, which is what, 128? Plus 4c plus d. Hopefully that looks right. And so now I have a system of equations. I have two equations and two unknowns. And if we solve this, what do we get? Did anyone solve it? So what do we get? We get c plus d is -4. And then 4c plus d is -19. C is -5. Okay, what else? What was D? 1. Okay, cool. Right, and again, you can all now see another place where we could make a question where all of a sudden you have to use linear algebra and matrices in order to figure out what the constants are, right? Okay, so now we know, therefore, f of x is 4x to the 5 halves minus 5x plus 1. And so if we want to know what f of 0 is, that's equal to 1. And that is b. Okay, makes sense? Any questions about that one? So just make sure you include that constant every time you take an antiderivative. Make sure, basically if you take two antiderivatives, you should get a linear sort of function here in constants. If you take 3 antiderivatives, you'll get a quadratic. 4 antiderivatives, you get a cubic. And in general, if you take n antiderivatives, you get this n-1 degree polynomial here. Okay, that's good. Okay, I'll assume it's good. Let me just duck out for a quick second and refill stuff, use the bathroom quick. I'll come back. We will go into office hours. Prep your questions. I've got one person, Agnes asked me a couple of questions. We'll go through those. Anyone else who has any questions, get them prepped up and we'll take them in a second. Aziz, are you taking off right away or do you get hang out for like
I'll hang out until you come back.
Okay, cool. Sounds good. I'll be right back, everyone.
Okay, so how prepared is everyone for this test? I know I asked this earlier, but no, only like one person answered me. Now I feel like when it's like the test is less than 3 hours away, I'll probably get a better answer. Barely? That's not good. Like there's something missing in my knowledge. I mean, if you covered all the material in the test information page, I don't see why you would say that, unless there's something you know specifically that you were not sure about. You don't know how to study, you just do them. The tutorials that will help actually are the last 3 tutorials. I mean, all the tutorials we did between last test and this test are obviously helpful, but I think specifically the last 3 tutorials we did, or 2 or 3 tutorials we did, were very, very helpful for sure. Yeah, there's definitely, I got a private question asking me, is there going to be optimization on the test? Yeah, definitely. There will definitely be an optimization question on the test. Too many stuff written in the test information. Oh, I mean, it's not that bad. Like to sum it up very quickly, realistically, it's everything to do with derivatives, like derivative law, like the rules and whatever. It's like logarithmic differentiation, implicit differentiation, and then there's optimization. I feel like that's pretty much sums it up nicely. I feel like I don't think I missed anything there. But you know, your derivative laws, everything to do with derivatives, implicit and logarithmic, and optimization. I feel like that kind of covers the majority of the topic here. I might have missed 1 or 2 small things, but it should be there, like in the information page. So like you can go through the information page relatively quickly and like scour through it and take the keywords. I think like some of it's over-explained a little bit, but it's mostly for your sake. It's over-explained. I mean, the best way, I got another private message asking like, what's the best way to study for tests? Honestly, like I feel like if you focus on like the tutorial questions and the questions we do, like you know, the lecture questions, the slides, we do all the questions there. And I would say more about understanding the logic of the question more than just solving it for the sake of solving it. It's important because I don't know if you guys noticed already, like in all the tests, you know, over the last like 4 tests, like what Tyler likes to do is take a concept, add a small twist to it, and see who can actually solve the question now. Like, so it won't be necessarily something that's like maybe copy paste from the textbook, obviously, because it's online. It's hard to do something like that. But it's like you take a current concept and add like a slight twist to it, and like make the functions rather than making a function explicit, make it arbitrary. Like use f of x and g of x instead of an actual function, just so you can't just put it on like a Wolfram alpha and solve it, right? And if you can break down the logic behind the question and see, like, actually understand what the material really is and how the topic really works, a slight twist and making a function arbitrary still doesn't matter. You can still solve it based on just understanding the concept well, right? So I'd focus necessarily more on understanding the concepts more than maybe just blatantly and blindly solving questions. Because if you solve something blind and then one input changes in the question, you might get lost, right? If you actually understand what that input means, you can actually translate that into your test a lot better.
All right. Okay, awesome, Aziz. Thanks. You can take off if you want. I got it from here.
Okay, awesome. I'm gonna head
Awesome.
out then.
Yeah.
Good luck.
Have a good weekend, man. See
Awesome.
you next week.
Yeah.
Okay, so for those of you in the I've gotten, I think, all of what you guys said. So Christian, both of yours I saw, Kelly, I saw yours, Curdy, I saw yours. Yeah, and Ariana, it's true. Like the test information does have a lot of stuff written in it, but it's just because it's really detailed, right? So I think this one probably looks like it's the biggest test just in terms of the test information and the stuff that was written down, but it's actually not that much more than normal. It's just that happened to be a little bit more detailed than it has been in the past. Okay, so let me just start plowing through questions here. All right, yeah, that's a nice one. So let me start off maybe like 610. So I think that was the first one. So 6-10. So it says, write down a function which satisfies each set of properties. This was actually a test question. So question A was f is continuous and everywhere differentiable. Okay. So if you saw this question on a test, what function would you give me? And I always say, give me the easiest one you can think of. Okay. So everywhere continuous, everywhere differentiable. Anyone? Okay, sure. Yep. So I've got x plus 1. I got e to the x. These are all good choices. There are even easier functions though, right? Like this is totally a legitimate answer. The zero function, the constant function, everywhere continuous and everywhere differentiable, right? Full marks. Okay, so B was, what does it say? Continuous everywhere, but not differentiable at -2. Okay, so continuous, let's say on R, not differentiable at x equals -2. Okay, so to answer this, sort of the easiest thing to do, I think, is to think of, can I think of any function which fails to be differentiable at a point? Like everywhere continuous, but not differentiable somewhere. Can anyone give me an example of such a function? And even if it doesn't satisfy this exact properties. Ooh, Davin, maybe. Okay, a couple of people have given me, it's okay, and Arslan, I like yours the most. So a couple of people have given me things with like, and Kelly, yeah, exactly. Okay, so I like a couple of these answers the most. Let me just kind of show you the one, and then let me address some of the ones that I got as direct messages. So the absolute value of x, right? We know that that thing looks like this, right? And it's everywhere continuous and not differentiable at 0. So if we want it to be not differentiable at -2, we're just going to rotate it a couple of units to the left, right? And so if we do the absolute value of x plus 2, that will work. Okay. Now there isn't only, right, there are obviously infinitely many solutions to this problem. So this is one of them. That would definitely work. Now, a couple of people mentioned things like that, you know, were things like 1 over x or 1 over x plus 2, right? So I got one of these, 1 minus x minus 2 over x plus 2. Problem is that this function is not defined at -2. And even if you did fill it in there, it actually has a removable discontinuity. Or sorry, it has an essential discontinuity, not a removable one. So anything that has an x plus 2 in the denominator probably isn't going to work. It is possible to make it work, but as a general rule, it won't. Denominator, you know, won't work. Okay. So that one is a little bit tricky. So just, you want to be careful with that, because again, this function fails to be continuous at -2, right? And we said it actually has to be continuous everywhere, just not differentiable at -2. Does that make sense, everyone? So for those of you who kind of like put that in, do you see maybe why that one wouldn't work? Right, because almost everyone who gave me one, your functions look something like, you know, at -2, they kind of like shoot off to infinity, maybe something like that. And it's got to be continuous, right? So that doesn't work if you do it. Oh, okay, sure. So, I mean, are you comfortable with why the absolute value of x is not differentiable at 0? Okay, sure. So let's just look at the limit definition. So if I were to compute the limit as h approaches 0 of so what we're going to do is let's just compute the one-sided limits. Okay, and let's just do the absolute value of x. Let's not worry about the absolute value of x plus 2 right now. Okay, let's just do the absolute value of x. So if I do the limit definition, so let's say f of x equals the absolute value of x. So this is going to be f of 0 plus h minus f of 0 divided by h. That's going to be the limit of the absolute value of h minus the absolute value of 0 divided by h. And we get this thing. Exactly, yeah, Davin, that might be a good explanation too. There's no tangent line for the absolute value of x, because on one side it wants to be +1 and the other side it wants to be -1. So at 0, it can't decide what it wants to do. It kind of wants to be both +1 and -1 at the same time, and it just doesn't end up working. But if we write out the definition for the derivative, we get this thing, right? And we saw this thing, remember when we were doing one-sided limits, as we approach h from the right, it's 1. Or as we approach 0 from the right, it's 1. And when we approach 0 from the left, it's -1, right? So this does not exist. Do you remember that sort of conversation, right? And we really talked about this when we were talking about like continuity and jump discontinuities and one-sided limits and these sorts of things. So if you try and compute the derivative of the absolute value of x, you get this thing, and that limit doesn't exist, so it's not differentiable. And then if you want to make it be not differentiable, instead of at 0, you want it to not be differentiable at -2. You just take the graph and you go and just slide it over 2 points, right? And so that's what we did here. Ooh, that's an interesting one. The problem there, so I got this question, would ln x work? So it kind of depends. So the question right now doesn't say it actually has to be continuous on all real numbers, in which case that function is certainly, like ln x is continuous everywhere on its domain. The only problem is that it's also differentiable everywhere on its domain. Do you know what I mean? Like that's sort of the issue, is that that function is also everywhere differentiable. Anywhere it's continuous, it is differentiable as well, right? So there's nothing sort of like, yeah. But I kind of see what you're saying. Like, it's almost kind of like a lawyer answer where you're like, well, it's not differentiable at -2 because it's not defined there. So it's kind of like a lawyery answer where depending on how literally we wanted to take the specifications, but I would say it wasn't in the spirit of the question. All right. Okay, so hopefully that makes sense. But if there's any sort of like outstanding questions, Agam, are you okay now? Does that make sense? Like if you just try and compute the derivative, it doesn't work out. Okay. C is f is defined at every real number. So it just says defined, but is not differentiable at exactly 2 points. So f is defined everywhere, not differentiable at 2 points. Okay, can anyone? So notice there's no condition that the function be continuous or anything, but the function does need to be defined everywhere, and it only fails to be differentiable 2 places. Can anyone think of something that you could do? And I think a lot of you are going to try and be fancy with this. Don't be fancy, okay? I don't want you to be fancy. I mean, that function's differentiable everywhere though, right? X squared minus 1 is everywhere differentiable. But maybe you want the absolute value of x squared minus 1. That would work. And Arsalan, yes, absolutely, a piecewise function can be used. So I do have a suggestion from one student, which is to take the absolute value of x squared minus 1. This does work, okay? Because if you plot this thing, it looks like, and so it fails to be differentiable here and here. I had a question, which is, can you use a piecewise function? The answer is absolutely. And if you use a piecewise function, can anyone think of maybe some way of doing this? So this example of the absolute value of x squared minus 1 is great because it's actually everywhere continuous and only fails to be differentiable at 2 points. Now that's actually much stronger than what the question asked though, right? All right, so how about this? Let's say, yeah, let's make this a little bit different. Let's say 100 if x equals 1 or 2 and 0 otherwise. Okay, so this function just looks like this. So it's everywhere equal to 0 but at 1, there's a hole at 1 and there's a hole at 2. And there, I just put little holes there, right? So do you guys agree that function is everywhere differentiable except at 1 and 2? Right? Like I just took a constant function and just plugged 2 holes in it and put those, replaced it with something somewhere else. And yeah, you're not differentiable there, right? There's no way you could be differentiable because differentiable functions are continuous and your function's not continuous. So in fact, this question equivalently could have been, give me a function which fails to be continuous at 2 points. Oh, this is a good one. Somebody asked, does this work? Right? And yes, I think it does. Yeah, I see no reason why that function wouldn't work. Again, it looks like a parabola, but it at 0 and -1 has these sort of like cusps, right? So it should look something like that. Yeah, totally, that works. Okay, so there's lots of possible answers. Really, this question is just like, can you come up with examples of things? I think it's a good little question. You guys don't have to get complicated. You don't have to give sophisticated answers. Generally, if I ask you to give me an example of something, I'm very happy if you give me the simplest answer you can think of. I can't overstate how when I asked people to do this, everyone gave me a complicated answer when this was a test question. And I'm like, no, just give me the 0 function. I would have been so happy if you gave me the 0 function. You know what I mean? Okay, so let me go to now 724. I'm going to skip 611 for now, and I'll come back to it if we have time. But 724, I think, will satisfy a couple of people because some people wanted like optimization questions and stuff. So 724. Oh, no, this is a graph question. Okay, I need to get the graph. So do I have my notes in here? I do not see my notes. All right. Hold on. I need the graph for this picture. So everyone, I'm going to look at 7-24. So you can go pull this up. This is a very visual question. So I'm just trying to get the graph itself so I can copy and paste it. But it's crazy that on this laptop, I don't have the notes. There we go. All right, let me reshare now. Nope, I gotta share my screen. Okay, and where do we want to go? I think we want to go to, let's just do it this way. All right, so here's the question. All right, so here are a bunch of graphs, and part A says, for which graphs is f prime of x greater than or equal to 0 for all x greater than 0. So how do I interpret this? What does this mean? If I'm looking for a graph where f prime of x is greater than 0, greater than or equal to 0 for all x greater than 0, what does that mean? Yeah, okay, well, not strictly increasing, but just, increasing, right? It doesn't, because it could be if f prime of x were equal to 0, which is allowed, if you're greater than or equal to 0, it wouldn't be strictly increasing in that case, right? It would be constant, but you're right, increasing. So this thing here means increasing if x is greater than 0. So if we look at these graphs, which of them are increasing when x is bigger than 0? Is graph 1, let's start at graph 1. Is this function getting bigger for x bigger than, yeah, non-decreasing is exactly how you'd say it. Yeah. So for graph one, is this function always getting bigger? Or is non-decreasing? What do you think? Anyone? Yeah, absolutely. Yeah, this one actually not just after 0, but this, like everywhere that you can see, this function is always just getting bigger. How about graph 2? Yeah, definitely not graph 2, right? Because you see here it's getting lower. So not graph 2. Okay, how about graph 3? Graph 3 is, right? And I think you mean, wait, Curdy, I'm not certain what you mean there. No, but not after x equals 2. It is actually increasing after 0, right? It's always getting bigger over here. It's not where is the function positive, it's where is its derivative, right? Yeah, so this one, it is actually getting bigger. Yeah, no problem, it's okay. Like I said, let's catch those now, right? So graph 3 is good. How about graph 4? Yeah, graph 4 is not either, right? It seems to be getting a little bit lower. Okay, so the answer here is 1 and 3. By the way, everyone, this was a term test question in person as well. So this was an in-person term test question, this exact one. So we're going to say 1 and 3 for this one based off of what we can see. Okay, does that make sense? Any questions about that before we go to the next one? Graph 4. So remember, you've always got to be getting bigger. And in graph 4, look at this part right here. You're getting smaller, and this part here, right? You're getting smaller. So if f prime is greater than or equal to 0, your function's always like getting bigger, right? It's never going to turn around and start going down. Your function's always got to be going up. And so that's what this question is asking. For which of these graphs is the graph always going up when you're to the right of 0? Yeah. Everyone else good too? Does it just need to be, it's just increasing. Yeah. So, because like here you can see in graph 1, you can see at this point, it kind of like it's flat. So if it was strictly greater than 0, then it would need to be strictly increasing. So you're right. In this case, it's not strictly increasing, it's just increasing. Or we might say non-decreasing. That's another way of saying that. Yeah. Okay. So I'm going to get rid of that. All right, so now on to B. So for B, we've got this f double prime is greater than or equal to 0. What does that mean in terms of like the shape of a graph? Concave up, okay? So we're looking for concave up when we're between 0 and 2. So let's look at graph 1 to begin. So if we look at graph 1, am I concave up between 0 and 2? Right, I switch, right? There are definitely parts where I'm concave up. I actually kind of, let me see if I can make my pen a little bit thicker. So it looks like maybe we're concave up here, but then we're concave down here, right? So we're concave down between 0 and 1. Concave down. And then between 1 and 2, maybe we're like concave up, right? So graph 1, I don't think is going to satisfy that, right? How about graph 2? Is graph 2 concave up between 0 and 2? No, it's not. No, look at this here. Let me highlight the parts where it's not concave up. These parts are concave down. Do you see that? Right? It seems to be like, even though it's not a full cup, you can see that it's starting to like, it's curving down. And then at about 1/2 and 3/2, it's concave up. So it seems to be concave up for some of it, but not for all of it, right? It's kind of like concave down there. Maybe I might be able to zoom. No, I can't zoom in because I'm in annotate mode. But yeah. Let me get rid of that. Okay, so that's good. How would it look like if it was? Well, there are a couple of concave up examples, or there is one. So maybe let's finish the question and we can ask it. So for graph 3, is this concave up between 0 and 2? Yes, it is, right? This portion right here is definitely all concave up. So this one, good. And then graph 4, all the tangent lines you draw are below the graph if concave up. Yep, that's exactly it, Davin. And right, so no for graph 4, because we've got this portion here, which is concave down. Right? Okay, so no to graph 4. So the answer for this is just graph 3. Everyone agree? Everyone's happy? What if it was turning from 2 on graph 4? What do you mean, what if it was turning from 2? What is that? I'm not certain what you're asking. So the inflection point is where the concavity actually switches. So at graph 4, it's not that the inflection is at 1.5, it's that there's a critical point at 1.5. The inflection point on graph 4 is actually at 1. Right? That's where it changes from being concave up to being concave down. Right? So it's like, here, let me try and draw it in blue. So the blue portion here is concave up. And then I don't know what color that is, green. The green part is concave down, and where we switch is the inflection point. So the inflection point here is actually at 1. And 1.5 is a critical point. It's where the derivative changes. Oh, if it was from 2, like you mean from 2 to 1? Oh, or if this was from 2 instead of 1? What do you mean from 2? Yeah, I'm just not quite certain what you're asking. It's concave down from 1. Well, from 1 to what? So from 1 to 2, yes, it's concave down. Right? And it's concave up from 0 to 1. And it actually switches every integer, right? So, and in interval of size 1, it switches from being concave up to being concave down. So from 2 to 3, it's concave up again. And you imagine that this pattern probably repeats itself. Right? So it just keeps switching concavity like constantly. And the points of inflection are actually at like 1 and 0 and or 0, 1, and 2 and 3 and stuff like that. Okay. So let's go to C now. So for C, for which graphs does f prime change sign between -1 and 1? Okay, so let's look at graph 1. So on graph 1, what does it mean to change sign? Does f prime change sign? If f prime changes sign, what does that mean? Right, changes from increasing to decreasing or vice versa. And yeah, Curdy, yeah, so in terms of like the actual sign of f prime, positive to negative or vice versa, right, negative to positive. And if we translate that into what the graph has to be doing, we're asking between -1 and 1, is it changing from increasing to decreasing? So if we look at graph 1, at anywhere between plus and minus 1, right, we're only looking between these lines, does it switch from increasing to decreasing? Well, right. Okay. So we may maybe make an argument at the points where it's flat, but in that case, at worst, it's just kind of like 0. But as Agam says, I think that like this is just sort of increasing, right? So the derivative is always greater than or equal to 0. I don't think there's any point where it's actually less than 0. The graph might be deceiving us a little bit, but you can imagine, I'm not going to ask you a question where it like actually dips a little bit just to be a jerk. So in this case, I would say graph 1 does not switch sides, right? So just increasing. Let's look at graph 2. So again, between plus and minus 1. Does it change from increasing to decreasing or vice versa? Yeah, for sure it does, right? It starts by increasing and then decreases, right? So increasing, decreasing. So graph 2 is good. How about graph 3? Yeah, exactly, sign change at 0. And so Davin actually bring up a great point, is you can detect a sign change because if it changes from being negative to positive or vice versa, it's going to have to go through 0 at some point, right? So that you're going to get that like horizontal tangent. So that's a great pickup there too, is that you can use that to help you determine that. So for graph 3, do I change signs? So I go from increasing to decreasing? Yeah, absolutely I do. And graph 4, yes, as well. Okay, great. So everything except graph 1, right? So 2, 3, and 4 for that one. Okay, for D, so I'm going to leave the lines on. What about the constant lines? So right, in those cases, so like the points where it flattens out, you mean? I'd say in those points, the derivative is 0, but it doesn't switch, right? So the derivative is positive, 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 goes to 0, but doesn't actually change signs, right? It never becomes negative. So it continues to increase again. In fact, for the purposes of this question, I would say you should assume graph 1 is just always strictly increasing, in that it doesn't actually flatten out, just because if we worry about whether or not the derivative is really 0 there, we could run into some trouble of just interpretation. Yeah, no problem. So for D, for which graphs does F double prime change sign? We're now asking, does concavity change, right? So let's look at graph 1. Does the concavity of the function change between -1 and 1? Yeah, I agree. Does everyone agree with Curdy as well? Like, it seems to be concave up in the beginning, right? It's sort of cupping upwards. And then at 0, it flips, right? And begins to concave down. So I would say yes to graph 1. Okay, graph 2. Yes as well, yeah, right? It's concave up in the beginning and at the very end, and then in between it's concave down. How about graph 3? Oh, I should get rid of the check mark on graph 3. Right, not on graph 3. On graph 3, it's just always concave up. How about graph 4? And yes, perfect. Okay, so everything except graph 3, right? So we've got 1, 2, and 3. Okay, and now finally, let's just do E. I'm going to let you guys figure out F, because if you can do E, you can do F. And I feel like we did something like this one similar in the poll questions to E, right? So F is the function in graph 1, right? So this is F. Which of these things is F prime? Anyone have a guess? Graph 2, okay. Can you guys tell me why? Like, what would you use to indicate that graph 2 was F prime? Yeah, okay, so it's saying if F is the function in graph 1, right? And I plotted F prime, is graph 2 F prime, is graph 3 F prime, is graph 4 F prime? See it, Theodore? Okay, yeah, okay, so both, yeah, Kelly, that's a great one. Davin, that's great. Yeah, horizontal line is tangent. So Christian, that's, I think, very similar to what Davin was saying. So Davin, let's use both of these. So Davin is saying it looks sort of like there are critical points here and here, right? And maybe at -3 and +3 as well. But either way, those are points where the graph of the derivative is going to be 0, or at least be close to 0. And this alone, okay, if we do this, we can kind of eliminate graph 3. Graph 4, you can probably say, look, there's no critical point at 0, so it's probably not graph 4 either. And so now you're done based off a process of elimination. Now, Kelly said something else, which is also great and also works, which is, oh, sorry, Kelly, you said critical points. I've got the two of you backwards. And Davin was saying that the function is never decreasing. So the derivative is always greater than or equal to 0. And if you look at these 3 graphs, which of them is always greater than or equal to 0? Graph 2 is the only one which doesn't, right? So all of these are great ways that you could determine what the derivative is. And absolutely, no matter which one you do, you arrive at graph 2 as being the derivative, right? And in fact, the derivative of graph 2, I guess this is part F. What is the derivative of graph 2? Exactly, graph 4. And we can do our critical point, like our little critical point check again, right? So where are the critical points? Critical point here, 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 here. Well, maybe not those last two. They don't quite look like critical points, but those are critical points. So they must correspond to zeros of the other function. And if we look at graph 4, we notice that this is exactly where the zeros are, right? So that tells us this is probably F double prime. And it's the only one that satisfies that. So it is F double prime. Okay. So that's how you do those things. It's just a matter of saying, like, what are the tangents on graph 4? So in graph 2, the blue things are where the tangent line is horizontal. Those must be the x-intercepts of the derivative, right? These are where the slopes are 0. So when I plot the derivative, it's at these points that I'm going to pass through the x-axis, right? These are going to be zeros of that function. Yeah, we're going to leave 611 for now just because there's a couple more questions ahead of it. So I want to try and give everyone a chance. Oh, and the tangents, so saying the tangents, like at -2, it's negative, at -1, it's positive, at 0, it's negative, so on and so forth. But I don't think we can say much more than that. Right, exactly. Sorry, yeah, the red, I think that is, the red things are the zeros, right, at -1 and +1. And if we look at the graph 2, we can see that our graph goes through 0 at those points. So it's exactly the same sort of idea. So the critical points are actually a really great way of determining a function and its graph. But Davin also brought up this great point for graph 2 being f prime, that it's always above, greater than or equal to the x-axis, right? So yeah, that's a cool thing, and we can use that to help us. It does, but notice graph 4 also goes through 0 at 0. And if we look at this, if we look at graph 1, this does not have a horizontal tangent at 0, right? And if graph 4 was f prime, it would need to have a horizontal tangent at 0. Does that make sense? So it can't be graph 4. Graph 4 can't be the first derivative because this would need to be horizontal here. How do you determine critical points? So Ruba, right now I'm just looking at the graph and trying to see, like, where is the tangent line horizontal? All right, so if I look at graph 3, for example, this looks like it's the only point. If I were to look at graph 4, I'm basically looking for those, like, those local minima and those local maxima, right? So the critical points are where I'm drawing, like, the horizontal lines. Do you see that? Like where the tangent is horizontal? Yeah. So remember, the derivative is the slope of the tangent line. So I got a question saying the horizontal tangent line is, the horizontal tangent thing is confusing. The derivative is the slope of the tangent line, right? And so where the slope is horizontal, that's the same thing as saying the derivative is equal to 0. Right? So the derivative is 0, and saying that the slope of the tangent line is horizontal is the same thing. And that's the relationship that we're using a lot here in order to be able to connect these graphs, right? Wherever the slope is horizontal on the original function, the derivative must be equal to 0. That's a great thing that we can use. What's not 0 in graph 4? Right, exactly. Yeah. Yeah, so in graph 4, the derivative goes, if this were the first derivative, it goes through 0 at 0, but it doesn't, this slope is not horizontal here, so it can't be the derivative, exactly. All right, so I've got 714 in the hopper. All right, let me get rid of this stuff. Oh, yeah, because I'm still in annotate mode. Clear all drawings and stop annotating. Okay. So 714 is a little nice implicit differentiation question. So for 714, we have x y cubed minus xy equals x minus 1. So part A is find dx dy, right? I think this was also a term test question. You guys seem to have like narrowed in on the term test questions. So find dx dy. Okay, so we're going to differentiate implicitly like we normally would, right? So we're going to differentiate d dy xy cubed minus xy is d dy x minus 1. And if we do this, we're going to get derivative of the first times the second plus the second times the derivative of the first equals dx dy, like this, right? And then we can solve this for dx dy. And so if I factor in dx dy and divide by y cubed minus 1, y squared, y cubed minus 1, like that. I forgot the xy. Oh, you're right. I totally forgot this term right here. So thank you for pointing that out. I just completely forgot about that. Dx dy y plus x equals dx dy. Yeah, you are right. I totally forgot about that term. Okay, so we're going to move all the dx dy's onto one side. So I'm going to get y cubed minus y minus 1 is equal to x. I shouldn't be trying to do this in my head, but I'm sure someone will yell at me if I screw up. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep. Okay. So dx dy is x 1 minus 3y squared over y cubed minus y minus 1. Does that look right? Did I get everything? Okay, that's good. Hope so. And then part B says, write x, there seems to be a typo here, write x as an explicit function of y by solving the equation for x, and then use this to compute dx dy. So I got a private message saying if we wanted dy dx, we would just flip it. Yeah, absolutely, right? So dy by dx would be y cubed minus y minus 1 divided by x 1 minus 3y squared by the inverse function theorem. Okay, don't forget to write that down. If you do this in the test, you need to say these words, okay, or you're going to get a mark deducted. So make sure you put that there. Okay, so B, right, x is an explicit function of y. So I want to solve this equation, xy cubed minus xy equals x minus 1. I want to solve this for x. So I'm going to put all the x's on one side. Y cubed minus y minus 1 is equal to -1. So x is equal to -1, y cubed minus y minus 1. And then we're going to differentiate it. Wait, sorry, I missed some messages. Do we have to put that whenever we do implicit differentiation? What, the inverse function theorem? Inverse function theorem is only when you flip the derivatives. So when you go from dx dy to dy dx or vice versa, you're using the implicit function theorem to say, look, if I were to have done this the other way, all I'd have to do is take the reciprocal. That's the inverse function theorem. And anytime you use a theorem, you should say what theorem you're using. So that's when you do it. Yeah. Does it have a minus sign for dy dx? It won't pick up a minus sign, direct messenger. Like you can just straight up take the reciprocal. You can take 1 over and flip the fraction. You don't have to add a minus sign or anything, if that's what you're asking. Okay, so now the question, so we've solved for x as a function of y. Now we want to compute dx dy this way. So dx dy. So we're going to use the quotient rule. So it's the top derivative of the top, which of course is nothing. Actually, maybe let's write this as like negative y cubed minus y minus 1 to the -1 like this. So we're going to get -1, well, -1. So y cubed minus y minus 1 to the -2 times the derivative of the inside, so 3y squared minus 1 like this. So this is going to be 3y squared minus 1, y cubed minus y minus 1, all squared, right? Okay, and so if we look at these two things, we say, oh, well, those are different, right? So if I look at this, and I look at this, I say those aren't the same. So something seems a little fishy here. But note the following. So they're pretty close though, right? The only difference is that this thing is squared in the bottom thing, and then there's this extra factor of x. So what we're going to use here is note that x is -1 over y cubed minus y minus 1. So therefore, I'm going to write this as 3y squared minus 1 divided by y cubed minus y minus 1 times 1 over y cubed minus y minus 1. This thing here is now equal to -x. So that gives me -x 3y squared minus 1 y cubed minus y minus 1. And these are now the same thing. Right? Okay, so Davin, you're okay though? You're saying now? Yeah, okay, cool. And so everyone sees that those are the same? Like the bottom one, right? If I take the minus sign and put it inside, you get the signs matching up. So that's part C. Okay. All right, now listen, class is done, but I want to do an optimization question because I was asked to do one. And I know somebody asked me for 720, but it's probably not the nicest optimization question. So let me do 723 because Kurt, you asked me for an optimization. I think Christian, you asked for it explicitly. Kelly, I guess you asked for 717. So Kelly, are you, actually maybe let me do 717A really, really quickly, because Kelly, you did ask, and I think I managed to skip you somehow. So 7-17, let me just do A here, okay? And Kelly, hopefully that'll be enough. So we've got here the function f of x equals, let me just write this as x to the 1/3 instead of the cubed root, because we're going to use that anyway, times 8 minus x. Now the critical points are where the derivative is equal to 0, right? So if we differentiate this, I have to use the product rule. So I'm going to get the derivative of the first thing times the second plus the derivative of the second times the first. And so this is going to be what? 8 minus x divided by 3x to the 2/3 minus x to the 1/3. And this is kind of gross, so let me give them a common denominator. So 8 minus x minus what? 3x divided by 3x to the 2/3. So that's going to be 8 minus 4x, 3x to the 2/3. Okay, so that's the derivative. Now the critical points are wherever the derivative is 0 or where the derivative doesn't exist. So what you want to do is figure out where's the numerator equal to 0 and where's the denominator equals to 0, right? So f prime of x equals 0 when 8 minus 4x, when the numerator is 0, which is the same thing as saying when x equals 2, and the denominator, so f prime of x, does not exist when the denominator is 0, which is saying, i.e., when x equals 0. Okay, so there are your critical points. So Kelly, does that make sense, like what I did there? And so you would do, the same sort of thing. Okay, sure. And if you want, I mean, there isn't a lot of time, but if you want to, you can like take a picture and throw it on Piazza. I mean, I've got to organize the test and everything, but I can try and take a look at it before then. But does that make sense? Like, does that help? Okay, cool. Okay, and now 723. So this is where I'm going to finish off today. So 723. So you work for Hydro 1. Interface with the following problem. Again, this was a term test question. So a transformer you built currently sits in a swamp and needs to be moved. And a new power line established. The transformer sits 6 kilometers from the road. All right, so here's our road. And then here's the old transformer. And this distance here is 6 kilometers. And must stay 6 kilometers from the road. Okay, so it's got to stay 6K. The nearest connection site is 8 kilometers away. So we have a connection site here. And it's 8 kilometers away along the road. All right. It will cost you $3,000 for every kilometer you move towards the connection site, right? That is, it will cost $3,000 for every kilometer between the old transformer and the new transformer. In addition, it costs $5,000 for every kilometer of power line you run from the new transformer to the connection site. Determine where you should move it. Right, okay. So I have to move the transformer horizontally. And then when I do move the transformer, I have to run power line to the connection site, right? So it costs me $3,000 per kilometer in this direction. And then it costs me $5,000 per kilometer for every power line that I have to, for the power lines that I have to draw, okay? So it says, figure out where the best place to put the transformer is. And it tells us that we should call this thing X, right? This distance here to be X. Okay, so we need to figure out if I move my transformer X kilometers, how much money is it going to cost? And I'd ideally like to be able to write everything just in terms of X, right? So my costs are equal to 3,000 X, right? Because that's how far I moved the transformer. But now I need to figure out how far is this? Is the power line, right? Because the power line is the dotted line here. So what I'm going to do is create, so I'm going to, in yellow, I'm going to put with the stuff that I'm drawing that isn't originally part of the question. So this is 6 kilometers. So if this is 6 kilometers, can anyone tell me what is this distance right here? On Piazza. Let me do it on Piazza site. Yeah, exactly. It's 8 minus X. Like basically, Simon, you're trying to make an argument for it being the inverse. And so it's probably easier. You can either just plug it in, like you get 2 answers, plug them in and see which one actually is the inverse. Does that make sense? Because you know, right, that, so everyone, this is just a side thing for Simon because he wants to run. So you know that this has to be true, right? That F composed F inverse has to just be X again. So once you get both of your answers, let one be the positive square root, let one be the negative square root, plug them both into F and see which of them actually gives you X out. Does that make sense? I know it's a lot of work, but try it and hopefully that will give you a clue as to which route you're supposed to take. Okay, cool. All right, so everyone, so I have here this triangle and one side is 6 kilometers. The other one is 8 minus X kilometers. Therefore, what is the length of the power line? Anyone? Pythagoras. Right? That line is the hypotenuse of this triangle, and therefore I can use Pythagoras in order to figure out how long it is. So that's going to be $5,000 times the square root of 36 plus 8 minus X squared. And like, does that make sense? Are there any questions about this? Because this is the crux. Like if you get here, you're done. Because at this point, you just find the critical points and you're finished. Does that make sense? Is everyone okay? So actually, let me call this the cost function like C of X. Okay, great. So we want to minimize the cost function, right? So we're going to compute the derivative. It's going to be 3,000 plus 5,000 times 1/2 times the square root of 36 plus 8 minus X squared times 2 times 8 minus X times -1, right? So we get 3,000. This 2 cancels that 2. So we're going to get minus 5,000 times 8 minus X divided by the square root of 36 plus 8 minus X squared. Right? And yeah, and so now we just set this thing equal to 0. Is this going to be a nightmare to solve? I hope not. Unless I forgot and did something silly. So this is going to be 3,000 root 36 plus 8 minus X squared is equal to 5,000 times 8, 8 minus X. Do I have to square both sides? Yeah, I don't think I'm going to be able to avoid it. So I'm going to get 3,000 squared times 36 plus 8 minus x squared is equal to 5,000 squared times 8 minus x squared. So without expanding this, that would be kind of messy. Why don't we just solve for 8 minus x squared? So I'm going to get, let's put all the 8 minus x squareds on one side. So, you could expand this at both sides. Oh yeah, you're right. I should probably divide by 1,000 squared on each side, right? So I'd get 3 times 36 plus 8 minus x squared is equal to 5 squared. Okay, I know what these numbers are. All right, 25, 8 minus x squared. And again, this is a good sign when you see 9 and 25, because you notice that like these are perfect squares, right? All right, so I'm going to get 9 times 8. So again, at this point, you just solve however you like. So I'm actually just going to solve for 8 minus x squared. So I'm going to get 8 minus x all squared times 9 minus 25. That has to be equal to negative 9 times 36. So again, let's just make this 25 minus 9 and then make that equal to that. So I'm going to get 8 minus x squared is 9 times 36 divided by 16. So 8 minus x is 3 times 6 divided by 4, which is what? 18 divided by 4 is 9 halves. So x is equal to 8 minus 9 halves, which is what? 18, so is also 9 halves. And there you get it. But like most of this is just algebra, right? You get like 90 or here is like 60% of the marks. And here is 70% of the marks. And then knowing that you set it to 0 is 80% of the marks. Oh, yeah, you're right. Yeah, you're right. 7 halves. So like, most of the marks are up to here. The rest of this is just algebra, right? And in fact, you can ask Wolfram Alpha to solve this if you want. You can be like, I asked Wolfram Alpha to solve this, and it told me x was equal to 7 halves. And we'd be like, yeah, that's totally cool, because we don't care if you can do algebra. We care if you know how to set the problem up. So does that make sense? Does everyone? What do you mean? What about the derivative? I mean, again, we should also check that this is a min, right? But I'm going to let you guys do that. Yeah, you could if you wanted to. I think, yeah, it's fair to say like by Wolfram Alpha, this is the derivative I got, sure. Because again, if I give you this sort of problem, we're more interested in can you set it up and do you know theoretically how to solve it? Like, oh, I'd find the critical points and then I would do such and such. What I don't want you to do, everyone, is I don't want you to say, I asked Wolfram Alpha what the min of this function is. I don't want you to do that, right? Because I want you to demonstrate that you know that you would find the critical points and do stuff like that. So I want you to be able to say, I differentiated using Wolfram Alpha. I found the zeros using Wolfram Alpha, but I kind of like want you to like list those steps for me. If you're not certain, just ask on Piazza. Okay, no problem, Arslan. Good luck tonight. That's going to take care of it. When we ask for implicit differentiation, dy dx for epsilon I, would it be, well, you'd have to, so Kelly, you have to chain or product rule that, right? So, right, like if you dy'd x ln y, this would be dx dy ln y plus x over y. In a fraction, do we find the critical points of the numerator and denominator separately? It's not that you're finding the critical points of the numerator and denominator. You're finding the zeros of the numerator and the denominator. And because that's where the numerator is 0, is where the whole derivative is 0, where the denominator is 0, that's where the derivative does not exist, right? Yeah, because critical points technically can occur where the function fails to be differentiable. Yeah. Same thing with the first derivative test, right? Just like the absolute value of x, right, is actually a minimum at 0, but the function's not differentiable there. So that's just why we include those points. Usually they're not useful and not worth looking at, but occasionally they can be minimums just because they're like the absolute value function, right? So that sort of thing happens. Okay, anyone, I gotta run just because I also have to set up the test and like monitor it this evening. So I, do have some stuff I gotta do. Hopefully I managed to help you out a little bit there. Good luck. Yeah, no problem, everyone. Happy to help. Good luck tonight. And don't, hesitate to ask on Piazza if you're not certain about something. Absolutely. Have a good weekend, everyone. Good luck on the test. And we'll see you next week. Okay? Ciao.